So pulling this back into the discussion of carbon dioxide and fossil fuel combustion. So we can write balanced chemical equations for the combustion of fossil fuels to look at how much fossil fuel is burned and how much carbon dioxide is emitted. Now, the fossil fuels that are burned are a combination of a lot of different hydrocarbons. So this is the first of a bunch of approximations or assumptions. We're going to use octane as a representative fossil fuel. So just now, we say that, and now this is an approximation, an estimate. So octane. Octane reacting with oxygen to form CO2 and water. And you look at these coefficients and you're like, those are big numbers. Yeah, that happens sometimes. But 2 times 8, there's 16 carbons here, 16 carbons there. 2 times 18, 36. 18 times 2, 36 hydrogens. 50 oxygens. Here we've got 32 plus 18, 50 oxygens. Balanced chemical equation. What this is telling us is that we get 16 carbon dioxide molecules for every 2 octane molecules that burn. Okay? But that's a very, very small scale, right? So we'll move that up to moles. The chemist doesn't. So we can also say that 16 moles of carbon dioxide are given off when 2 moles of octane are burned. Okay? So the coefficients in the balanced chemical equation gives us the molar relationships. 2 moles of this plus 25 moles of that gives me 16 moles of this and 18 moles of that. So when you look at a balanced chemical equation, you can just sort of mentally insert the unit mole here. The coefficients are exact numbers because they come from actual numbers of particles interacting. So the amount of every substance that's used and every substance that's made, they are related to the amounts of the other substances. So we see the law of conservation of mass is observed here. We balance the equation by balancing the atoms. And then when we're studying the numerical relationship of chemical quantities, this is called stoichiometry. So that's a big word, stoichiometry. Okay, so let's take this away from burning octane and talk about pizzas. Making pizza. So making pizza, cooking anything, the amount of things you can make, the amount of pizzas you can make depends on how much stuff you have, right? So here we're using a very, very simple equation, recipe for pizza. 1 crust, 5 ounces of tomato sauce, and 2 cups of cheese, and that makes 1 pizza. So we can express that mathematically and say there are ratios. 1 crust to 5 ounces of sauce to 2 cups of cheese to 1 pizza. And we can use this to calculate how many pizzas can we make if we had 10 cups of cheese. Now, you can probably do that in your head, but the point of this is that you can do it in your head, and we're going to see how we do it mathematically as well, because when we do octane and CO2, it doesn't work out so well in your head, right? So this is where dimensional analysis becomes super, super important, makes all of this much easier. So we want to know how many pizzas can be made from 10 cups of cheese. So I'm starting with 10 cups of cheese, and the question is, how many pizzas? And what's the relationship? How do I change this unit from cups of cheese into number of pizzas? I need a relationship. Well, I have this relationship here. There are 2 cups of cheese for every 1 pizza. So this can be done in 1 step. 10 cups of cheese. I'm going to pizzas. That's my unit. And down here, I want cups of cheese. And I put those in so the units work out. And then I look at the balance equation. There are 2 cups of cheese for every 1 pizza, 2 cups of cheese for every 1 pizza. So I end up with 10 divided by 2, which is 5 pizzas. Any questions? Some of you still struggling with dimensional analysis and still not writing a path. Write the path. It makes everything so much easier. And if you're struggling with it, please come and talk to me, and we'll go over it and figure it out with you until it clicks. And like one person said yesterday, oh, that's easy. Because she saw it. Once you see it, it is easy. Until you see it, it's not. So the ratios of coefficients act as conversion factors in balanced chemical equations. So we can answer questions like, if we burn 22 moles of octane, how many moles of CO2 form? So we're going from, starting with 22, well, let's be careful with that, 22 moles of octane. And we want to know moles of CO2. Well, the balanced chemical equation gives us the relationship in numbers of molecules or in moles, right? So 2 moles of this gives 16 moles of that, so this can also be done in one step. 22 moles of C8H18. I'm going to have one fraction. I'm going to moles of CO2. I'm going to put moles of C8H18 down there so they cancel out. And now the units tell me where to put the numbers. The numbers for this mole ratio come from the coefficients in the balanced equation. There's a 2 in front of octane, and so I put a 2 moles of octane. And there's a 16 in front of CO2. So again, we can imagine that there are units of mole in here. We have to use counting units. Any questions? Well, we don't usually measure things in moles. We measure things using mass. So we start with a mass of substance. The chemical equation gives us mole ratios. And so we start with mass, but we have to convert to the amount in moles. Then we can use the balanced chemical equation to convert to moles of the thing we're interested in. And then we use molar mass to convert back to grams. So this is the general plan for stoichiometry. And I tend to think of it as grams to moles to moles to grams. That's the starting point for stoichiometry. We'll change it up a little bit. We'll cut the end or the beginning off or change the units, but that's the starting point. And you'll see that moles are in the middle, right? So grams to moles to moles to grams is the starting point. And you know that you're getting it when you wake up in the middle of the night muttering grams to moles to moles to grams, right? Get in there. So now we can do a problem like this. According to the U.S. Department of Energy, the world burned 3.3 times 10 to the 10th barrels of petroleum in 2013, the equivalent of approximately 3.7 times 10 to the 15th grams of gasoline. Calculate the mass of CO2 emitted into the atmosphere using the combustion of octane as the representative equation. I like to use this balanced chemical equation to organize the information and help me decide what am I starting with and where am I going. So I've been given this barrels of petroleum, and it says that is equal to about this many grams of gasoline. And we're using combustion of octane. So we're saying if the gasoline was pure octane, this is how much CO2. So there's a bunch of approximations in here. So this one is a little fuzzy in that it's not obvious necessarily. We're talking about this is the mass of octane. So that's the mass of octane. I'm going to write its number under octane in the chemical equation. So 3.7 times 10 to the 15th grams of octane. And what am I trying to figure out? Calculate the mass of CO2, right? Okay, so here's CO2. I'm going to put a question mark there. And mass, probably grams would be a good unit, right? So I've identified my starting point and my ending point, and now I can map out a path of how to get there. So grams to moles to moles to grams is probably what we're going to need. So grams of this, 3.7 times 10 to the 15th grams of C8H18. I'm going to convert that to moles of C8H18. Grams to moles. Then to moles of the thing I'm trying to find. Convert that to moles of CO2. And then to grams of CO2. Grams to moles to moles to grams. In these equations, these problems, it's very important to put the chemical formula there because moles of C8H18 are not the same as moles of CO2. What we're doing here is we're changing one thing. Here I'm changing the unit from grams to moles, but I'm talking about the same compound. In the middle, I'm keeping the same unit, moles, but I'm changing the compound. And at the end, I'm going moles to grams, changing the unit, but not changing the compound. We just change one thing at a time, just one thing. The middle conversion is the mole ratio from the chemical equation. The first step and the last step we've already done. That's the molar mass, converting between grams and moles. So any questions about how I got the path? Now we're going to follow the path just like we followed the path for all of the other dimensional analysis problems. I look at this and I see 3 arrows. I'm going to have 3 fractions, and I'm just going to write the units in. 3.7 times 10 to the 15th grams of C8H18. 3 arrows, 3 fractions. Grams C8H18 to moles C8H18 to moles of CO2 to grams of CO2. I took my path, and that becomes the tops, the numerators of all of my terms. I just copied it down. I need my units to cancel, so I'm going to take this unit and bring it down here so it'll cancel out. So grams will cancel. Moles of C8H18 down here. It's going to cancel. Moles of CO2. That's going to cancel. Units in place. Now I go find my numbers. The moles in the middle here come from the balanced chemical equation. Up here I've got moles of CO2. So I look here, here's CO2, there's a 16. So I'm going to write 16 in here. Down here I have C8H18. There's C8H18, it's got a 2 in front of it. I'm going to write a 2 in front of it there. just pulling those numbers down. Then I need molar masses, so I'm going to have to calculate those. So for C8H18, I've got 8 carbons times the mass of carbon, and 18 hydrogens times the mass of hydrogen. Calculator gives me 114.224. Thinking ahead about significant figures, my starting number only has 2 significant figures. That's going to limit my answer, and so having some extras here is not going to hurt anything. You can round it if you want to. So 1 mole of that, 114.224. And then for CO2 is carbon plus 2 oxygens. So that's 44.01. 1 mole of CO2 weighs 44.01 grams. Any questions? So then, start at the left and move across, multiply by the top, divide by the bottom. So 3.7 EE15 divided by 114.224 times 16 divided by 2 times 44.01 equals 1.140 times 10 to the 16 grams of CO2. I could simplify 16 halves to 8, but why? I might screw it up. Just use the calculator. I've got to get it out anyway. I started with 2 significant figures, so my answer is going to have 2 significant figures. 1.1 times 10 to the 16th grams of CO2. And these numbers like this are just, they're hard to determine if they're meaningful or not. They're just really, really big. Any questions? So let's compare the results here. So we just calculated that petroleum combustion produces about 1.1 times 10 to the 16th grams of CO2 per year. And for all the approximations that we've made, 2 significant figures is probably pretty reasonable. Volcanoes produce about 2 times 10 to the 14th grams of CO2 per year. So volcanoes don't produce as much. How can we make a meaningful comparison here? Well, maybe find out how many times bigger the one is than the other. So 1.1 times 10 to the 16th grams per year divided by 2 times 10 to the 14th grams per year. $55. So by these estimations, human combustion of fossil fuels produces 55 times more CO2 than volcanoes. That's a lot. That's a big difference. This isn't like 1.5 times or something. 55 times. So combustion of fossil fuels is definitely putting a lot more CO2 into the air than volcanoes. Does that mean that humans are responsible for global warming? Not necessarily. Like I said, there are people who argue that global warming is not actually happening. Let's do another example. Magnesium hydroxide, the active ingredient in milk of magnesia, hence the name magnesia, neutralizes stomach acid, primarily HCl, according to this reaction. What mass of HCl in grams is neutralized by a dose of milk of magnesia containing 3.26 grams of magnesium hydroxide? So this is a chemical reaction that might occur in your stomach when you take an antacid. So what mass of HCl in grams? That's the question that's being asked, right? So again, I'm going to use my balanced chemical equation to organize the information. What mass of HCl? So question mark under the HCl, and the unit that's requested is grams. And then it says we've got milk of magnesia containing 3.26 grams of magnesium hydroxide. So I'm going to write that under the formula, 3.26 grams. So I have one number that I'm given, and I'm asked for another number, and so I need to come up with a plan, a path to get from one to the other. 3.26 grams of MgOH2, and I'm trying to get to grams of HCl. What do I put in the middle? Moles. Grams to moles to moles to grams. So I'm starting with grams of magnesium hydroxide. I can use the molar mass to convert that to moles of magnesium hydroxide. Using my balanced chemical equation, I can convert moles of magnesium hydroxide into moles of HCl. And then using the molar mass, I can convert moles of HCl into grams of HCl. And I think some people wonder, well, isn't there a shorter way to do this? Not really. Not really. This method can be applied to any chemical equation, right? And so you learn this method and you can solve all the problems. So again, I have 3 arrows. I'm going to have 3 conversion factors. So I start writing my equation by putting in the units first. 3.26 grams MgOH2 times and a line, times and a line, times and a line. One of each, one line for each arrow. And then the units, grams magnesium hydroxide to moles magnesium hydroxide to moles of HCl to grams of HCl. So I'm just copying down the units from my path. And then the units in the denominator, I take the previous unit. I want grams of magnesium hydroxide to go away, so I'm going to divide by that. I want moles of magnesium hydroxide to go away, so I'm going to divide by that. And then moles of HCl. All the units in place. Now they just tell us where to put the numbers. There's so much less thinking to do here. So in the middle, the mole ratio, those numbers come from the balanced chemical equation. What number is in front of HCl? So 2. 2 moles of HCl, so 2 moles of HCl. What number is in front of MgOH2? An understood 1, right? It's not written, but we understand it to be a 1. So I could leave this as an understood 1, or I could write a 1 in there, whichever makes me happier. And then I need molar masses. Chemists calculate molar masses a lot. So for MgOH2, we've got magnesium 24.31. And OH2, so the OH is a polyatomic ion hydroxide in parentheses with a 2 on the outside. So that means there's 2 of everything in there, right? There's 2 oxygens and there's 2 hydrogens. So 2 oxygens and 2 hydrogens. .326. There will be questions on the exam today where you have to calculate a molar mass like this. And I highly encourage you to write this out. Write down the numbers and then punch them in your calculator. That way you can come back after you've finished all the questions, you can come back and look at your work and double check, right? So that's grams. 1 mole of magnesium hydroxide is 58.326 grams. That should probably have 4 significant figures. And then HCl is 1 hydrogen and 1 chlorine. 36.458. So here grams on the top, so 36. And a 1 down here. Got all my numbers in there? Now I multiply and divide. 3.26 divided by 58.326 times 2 times 36.458 equals. As is often the case, my starting number had 3 significant figures, and the things I've used in the middle are either exact or have 4 significant figures, and so the answer is going to have 3 significant figures like the starting number. So I'm going to write down the answer with a couple of extra digits and then round it for my final answer. Any questions? .08. Got it right. Here's another example. Component of acid rain is nitric acid, which forms when NO2, a pollutant, reacts with oxygen and water according to the simplified equation. The generation of the electricity used by a medium-sized home produces about 16 kilograms of NO2 per year. Assuming that there's adequate oxygen and water, what mass of HNO3 in kilograms can form from this amount of NO2 pollutant? Okay, so there's like a story hidden in there. We don't need the story to solve the problem. It's just trying to make it relevant. There's one number in there, right? 16 kilograms of NO2. So in my balanced chemical equation, I'm gonna write 16 kilograms under the NO2. And then the question is, what mass of HNO3 in kilograms? So HNO3 is over here. So question mark, and they want kilograms. And all those other words, just words, so many words. I'm going to write the path at the top this time. So 16 kilograms, what's our thing we chant? Grams to moles to moles to grams, right? Well, this is kilograms. There's a couple of different ways we can handle that. But can we convert kilograms into grams? Sure we can. So we can go to grams of NO2. and we're trying to get to kilograms of HNO3, grams to moles to moles to grams, so grams of NO2 to moles of NO2 to moles of HNO3 to grams of HNO3 to kilograms. Wasn't quite enough space. So you can add a term at the beginning and the end of your path and write it all out. That's absolutely fine. You can say, well, that's awfully long. I'm just going to convert my kilograms to grams before I write the equation and do it that way. But then you have to convert back at the end. But I'm going to show you something else. So I'm going to kind of lump these together and sort of lump those together. And I'll show you what I mean. So we're going to start with 16 kilograms. I'm going to write the kilo in red. Kilograms of NO2. What I'm going to do is I'm going to just leave the kilo there. So kilo means times 10 to the third. I'm not going to cancel it out or do anything with it. I'm going to leave it alone. And it'll still be there at the end. And it'll make my answer be in kilograms. So it's red. We're just going to ignore it. So 3 arrows, 3 factors. So grams of NO2 to moles of NO2 to moles of HNO3 to grams of HNO3. We got moles down here. And I've got moles down here. Down here I've got grams of NO2. That's going to cancel grams of NO2. It's not canceling the kilo. The kilo is just sitting there. We're ignoring it. Okay? Yes, you can just do that. Because it is times 10 to the 3, right? So if we wrote this as 16 times 10 to the third grams, do we have to cancel out the times 10 to the 3? No, we don't. Like I said, if you want to put an extra step at the beginning and the end and do that, write it all out, absolutely you can do that. They're going to cancel each other out. Okay, so moles in the middle here. HNO3 has a 4 in front of it. So I'm going to put a 4 in front of HNO3. And NO2 also has a 4 in front of it. So I'm going to put a 4 there. Then I need a molar mass of NO2. So that's 14.01 plus 2 times the mass. Well, that's sloppy. 2 times the mass of oxygen. So 46.01. So 1 mole is 46.01 grams. And then at the end, I need the molar mass of nitric acid, which is 1 hydrogen and 1 nitrogen and 3 oxygens. .018. 1 mole, 63.018 grams. So I'm going to take 16 divided by 46.01 times 4 divided by 4 times 63.018. And I'm getting this number, 21, and I'm looking at sig figs. My starting number only had 2 sig figs. So this is going to have 2 because in the middle I had exact numbers and I had 4 sig figs. So 21.91. I've got grams of HNO3 and I've got that kilo that I didn't cancel out. So then I'm going to say that this answer is 22 kilograms of nitric acid. Any questions? So grams to moles grams is the regular stoichiometry. This problem got mixed up a little bit because it was kilograms at each end. And there's different ways to deal with that. And we'll see throughout the semester some other variations of this problem. Yep.
So you were able to end up with kilograms because it was never canceled out, so it
Yes.
was transferred over,
Mhm.
right? Okay.
Yep, I ended up with kilograms at the end because I never canceled it out. You could add a term in here that's 1 kilogram and 10 to the third grams so that the kilo would cancel out there. And then over here, you're going to need a term to get kilograms in the top, and you're going to have 10 to the third grams in the bottom, and those 10 to the threes cancel each other out.
I would have thought it would be wrong somehow.
Another thing you can do that it saves you at least one step is anytime you have a number and a unit with a prefix, instead of writing the prefix, you can write what it means. So you can call this 16 times 10 to the third grams. It's not proper scientific notation, but your calculator doesn't care. And so you can instantly convert into the base unit without really doing a calculation at all. So you could stick that in down here and go through, and then you'll end up with grams and you'll have to convert to kilograms. .22 kilograms